Okay, so when I post the grades on Connect, can you see them? Ah, okay, so it's okay. I wasn't sure if you can see them right away or not, so I brought back the assignments. There are some comments on the assignments, but not too many, because I had the same comments for all of you, so I thought I may as well say it instead of writing on each page the same comments. So in general you did well. The main complaint is that you didn't think of the most practical solution. For example, there were some solutions which technically could work, but are very impractical, like because of the first question with the weather or the first question with the blood. I'll give you an example on the blood flow sensing. Some of you said you'll build a little propeller in the needle of the syringe, and the blood will turn the little propeller, and there'll be a little encoder or a laser, but that's very impractical. Because if the syringe is less than a millimeter, if the hypodermic needle, the propeller will have to be half a millimeter, and in reality it's not going to turn. The reason why it's not going to turn is because it's issues of viscosity. This propeller has a shaft which has to go through the needle, so there's going to be, because of viscosity of blood, so there's going to be way too much friction in that shaft that this half a millimeter propeller can turn it. Okay? So some of you answered the solution which theoretically could work, but it's very impractical. If you built it, it would never work. So what I did, whoever answered correctly and reasonably practical got 10 out of 10 points. Whoever answered something which is technically correct but impractical got 9 out of 10 points. Now whoever made mistakes started getting less, 8 out of 10, 7 out of 10. For a typical mistake, some people said they'll measure something in the hypodermic needle with a capacitive sensor. Like they'll have some cantilever, the cantilever will deflect by blood flow, they'll put a capacitive electrode, measure the deflection, but of course blood is a conductor, because blood has salt in it, right? So you can't have a capacitor in blood, because the blood will short it out right away. I mean, even normal water is a conductor because it has a bit of ions, right? To make water non-conducting, you need special water, deionized water, but blood has 0.9% salt. So blood is a complete conductor, shorts out everything. Okay, so if you did something like this, you lost a point. But altogether, the whole thing is only 10 points of your final, but I just want you to know what to do in the next assignments. So it doesn't have, so don't write something which theoretically doesn't have a flaw in it, but will clearly not work when you build it, right? So think of it. So you have to think as if you are solving a real-life problem, not just an academic paper. So again, if you talk about the measurement of the river, and I emphasized up north, which means the river will have ice on it, will have logs on it, will have winds on it. So so don't propose a solution which some delicate thing floats on the water, because it will be swept away instantly. Although again, theoretically it's correct, but if you propose a solution, something floating on the river, you have to show how you protect it. And some of you did that. Some of you actually had a very reasonable solution, not the best solution, but reasonable. They said, if this is a cross-section of the river with the water, what I'll do is I'll put a pipe in the river, a pipe with holes. So the water level inside the pipe will be the same as in the river, but inside the pipe there is no ice, no storms. Now inside the pipe I can have a float, and I can use sonar and do whatever. Okay, so either a pipe or a well next to the river and connect them, but the simplest is put in a heavy steel pipe in the river and do the measurement in the pipe, which is connected to the river. So that whoever did that got full marks. It's not the best solution, but it's practical. Whoever said I'll just have some float and do some stuff lost 1 point, because it's not what the question asked for. The question asked for some very rugged solution. Okay. So let's talk about what would be the best solution. I was surprised that none of you hit on the best solution, although some of you came close, because the better solution is submerge something inside the river, like a pressure gauge on the bottom. So this is a river. if you put a pressure gauge on the bottom, you can know the depth of the water. Okay. Some of you picked up on the fact that it's not deadly accurate because the water changes density with temperature. As you know, at 4 degrees it's densest. So if you want to have a pressure gauge, maybe a better solution is to have 2 gauges, so you can subtract all the environmental issues like the temperature of the water, density of the water, barometric pressure, right? Okay, so some of you, actually quite a few of you, correctly figured out that instead of just 1, the best thing is to put 2. So you put 1 at the bottom and 1 at, let's say, 4 meter, because the river minimum, the minimum was 5 meter. So if you put 1 at 4 meter, it will never be exposed to the weather. So now you have P1 and you have P2, okay, and you can scale it because this is 4 meter. So P2 minus P1 is equivalent to 4 meter, and now you measure P2 and divide it by this. So what you do P2 divide by P2 minus P1. So now you have a system which is, it's similar to a differential system, right? It takes out all the non-measured variables, because if the water gets denser, it doesn't matter. Well, you can split hairs saying there's a gradient. Inside water there's a temperature gradient, but this is already second order effect, because if you calculate that, gradient meaning that typically water at the bottom you get 4 degrees C because it's the heaviest water. But if you calculate how much this gradient will affect the error, and you can see it's much below the error I stated. So the ones who are perfectionists actually added some comments that you can calculate that. Okay? But if you do it this way with 2 pressure sensors, it takes out air temperature, water density, takes out all the errors. So, but this is still not the best solution. So that is the best anybody here got. Okay, but to be practical, there's better solutions. First problem with that, you have some electrical wires going into water. And whenever you have electrical wires going into water, it's a really very difficult problem, because I don't know if all of you are aware that a normal plastic insulated wire or rubber insulated wire is not waterproof. Water will slowly seep through it. Okay? Because only ceramic and metal are hermetic. So, and all plastics are not hermetic. Now, some plastic resist water for many, many years, but it's actually not so simple to make something truly waterproof which will last forever. The way it works, you can buy submersible pumps and you can buy other things. It just works on the fact that the water will eventually seep in through the insulation, but it will be negligible. The leakage of the water will be negligible compared to the power. So say if you have a pump and the water eventually leaks through the insulation and causes a leakage of a microamp, in a pump it doesn't matter, the pump takes 10 amps, right? But if you have a sensor, if you leave it in water with a plastic cable, eventually there will be a leakage inside of a microamp, and if the whole sensor works on a milliamp, then you already get a measurable error. But it can be done, but it is much, much better to do 2 things, and I'm surprised nobody here came up with it. The first thing is put 2 floats here, just like this, but bring out tubes straight from the floats and measure the air pressure outside. So if you do the same thing as you did with some differential pressure gauge, okay, but don't try to measure inside the water. Just take a very thin hose, like a plastic hose, connect it to this bladder. So you have 2 bladders here which are also act as a floats. So you have here is same as here, you have P1 and P2, but all the measurement is done outside the water. So that makes much more sense, right? You don't have to worry about eventually water leaking into it. If you have to do maintenance, you don't have to drag the whole thing out of the water because it's anchored at the bottom of the river. Here all the maintenance is outside. Okay? Now, and the second thing that 1 or 2 of you picked up, that it's not a good idea to put the second sensor right at the bottom. Because at the bottom of the river there could be silt build up, and eventually it could cover the sensor, wouldn't be accurate. Okay, so the best idea is actually to float the lower sensor just a little distance, and this is a known distance because you build it. So when you build the thing, you make an anchor, you make a cable, and you put 2 floats on it, and the first float is a given distance, say 1 meter, and the second float is, let's say, 3 meter. So it's still all accurate because you can always add 1 meter to the result. Now this way you are not worried about rocks falling in, silt, dead fish, whatever, covering the bottom sensor. Okay? So the absolutely best solution is, again, do a differential system which takes out all the errors of water density, but don't start from 0, start from 1 to get rid of unknown bottom. Bottom could also be very soft, so when you put the weight in, it could sink into the silt, right, with the sensor. So you want to do, and don't put the sensing in the water, put the sensing outside. Okay? Good. Now, on the second problem, measuring the blood velocity, most of you gave reasonably good answers, and there is 3 methods that were suggested, I would say, equally. A third of you suggested just cooling effect. If you put in a hypodermic needle, you can put some kind of a wire which gets heated electrically, and the blood cools it. Okay? And that is not a bad solution. You can do it 2 ways. You can actually do it by measuring the resistance, running it at a constant I, and measuring delta V, which is proportional to the resistance. You can also do it in a slightly more elaborate way, that you force this to be at constant temperature by closing the loop with an op-amp and measuring the power. Because the more flow there is, the more power you'll need to measure it at constant temperature. Okay? The main advantage of this method, you can make it as tiny as you want. Because this resistor could be a teeny coil of wire. Okay, you can even use regular copper wire, and it's no problem at all to fit it through a needle. In one of the earlier classes, this was their term project. Each one got a needle and a piece of wire, and they had to build that. Okay? Your term project will be different, but actually it worked very well. The students had no problem to winding a teeny coil, putting in the wire, and calibrating it. So this a good thing about that you can make it as small as you want, even quarter millimeter. Okay, some of you suggested a second method, which is quite reasonable, taking advantage of the fact the water is conductive. So if you have a magnetic field, say you can put the arm or the leg in a big magnet, and let's say you have a magnetic field going into the board. Okay. And if you have 2 electrodes, so again you have an hypodermic needle, and the hypodermic needle has 2 electrodes on it. And the electrodes come out, and you have a blood flow. So that is the same as moving a conductor in a magnetic field, and it creates a voltage, and it's the same basically BLV, because this is B, this is L, and this is V. Okay? And this method was actually used to generate power. Here we're just looking for a teeny voltage, and if you calculate, you will get enough voltage, because B could be like 0.1 Tesla, L we said 2 meters per second. That is a V, sorry, that's a V. Okay? And 0.1 Tesla because it has a big air gap. Unless you go in an MRI machine, you don't have much more than 0.1 Tesla. So this is B, this is V, and L, let's say half a millimeter. So 5 times 10 to minus 4 meter. Okay? So what you're talking about is this times this times this is 1. So you're talking about 0.1 millivolt. Okay? It's not a lot, but 0.1 millivolt, especially at low frequency, is completely measurable, because you can filter it. The blood velocity doesn't change that fast. You can filter it at 1 hertz or something, so it's completely measurable. Okay? Here the signal will be bigger. How big the signal will be depending on the resistor. If you take a thermistor has a huge change in resistance, then you'll get a huge change here. signal will be volts, not just millivolts, but volts. If you take a nickel wire, which is about the best of the metals, you will get many millivolts. If you take a copper wire, get a few millivolts. Okay? So this has a very large signal. If you took a thermistor, it wouldn't need an amplifier. This will have, as you see from the calculation, 0.1 millivolt, but it's quite reasonable. And the third method people suggested, which is quite reasonable, is to put in two needles and inject something with one needle you can detect in the other needle, and typically you inject a shot of cold saline. This is actually used in hospitals. You inject one drop of very cold salt water, because salt water you can mix with blood. It's the same concentration of salt, the same 0.9% NaCl. Okay? So you inject a drop of cold water, you know this distance, and here you have a thermistor. So when you look at the thermistor, you will see this. This is T0. After a certain time, the cold water will reach here, there will be a drop. Temperature, you measure the time. That's a very accurate method, but it needs two needles. So anybody who suggested any one of those three got full marks. Now, some people suggested Doppler, and that's problematic, because for Doppler, of course, if you go straight like this, it wouldn't see Doppler. You have to go at an angle. But if you go at an angle, it will depend on the angle. The accuracy will depend on the angle. Now, the blood vessel is not straight. So when you put it in a blood vessel, you really don't know at what angle you're putting it in. Some people also suggested laser interferometry, but all these methods depend on exactly knowing the angle. Okay? You can do some tricks with Doppler, but still these things are sensitive to angle. The blood vessel can be curved, and you really don't know the dimensions. So Doppler is not bad, but it's a bit more problematic. Laser interferometry and imaging is very problematic because the blood is opaque. You cannot and the blood is diffusing. If you shine a laser beam through the blood, nothing comes out because blood is full of little particles, which are the blood cells. So you can't do imaging, you can't do lasers, everything spreads right away like a glow. Okay? So whoever suggested that, like imaging with lasers, lost 1 point because it's really not practical. Okay, so these are the three solutions. And this is not bad at all because it's cheap, simple, big signal. Just by coincidence, I'm involved in several medical companies, and one of the medical companies is called Cardium. And what Cardium does, they put something in the atrium of the heart, which expands into a sphere with 200 electrodes, and it measures the blood flow everywhere. And once it measures the blood flow, it knows the map of the heart. Because when you do ablation in the heart, or anything in the heart, you have to know where you are, because otherwise if you burn or cut the wrong thing, you're dead. So the most important thing is to map yourself, to orient yourself, to know exactly where you are in the heart. So the way the Cardium system works, you put in a thing through the leg, like a stent. It opens up into a mesh, because it has to allow blood flow, so it can't be a balloon. So it opens up into a mesh. The mesh has 200 of these thermistors. It just is covered with thermistors. Also has 200 ablation electrodes and 200 voltage sensing electrodes. But the first thing it does, when the mesh opens up, it measures the flow, blood flow at 200 points. From this it knows where the valves are, where the pulmonary arteries are, pulmonary veins, because the flow map shows you the ports, right? You see the big mitral valve, you see, and then the software kind of rotates the image and makes it fit the heart. Because imagine if you have a sphere and you know the sphere has to have 2 holes here, 1 hole here, where the valves are. So once you know where the holes are, you know where you are in the heart. And then the ablation electrodes start doing all kinds of things in the heart. So it's a very complex system, but the backbone of the system is the automatic orientation inside the heart, because you cannot use a camera because the blood is opaque, and this works very, very well, and that's exactly how it works with this expanded mesh, which has a bunch of the sensors, and these are done just with copper. These are done just by the PCB. These are very narrow PCB strips, and there's just a trace which does like this. Okay, and you just measure the resistance of the PCB itself, because there is enough the PCB meanders so to get a few ohms, and that is sensitive enough to detect 0.1 degree. Like, it's accurate and sensitive to 0.1 degree, so you can map the flow very well, because the flow in the heart is actually in the range I gave you in the question, 0.2 to 2 meters per second. So this works very, very well. So to show you it's practical, it's not just an exercise, this simple idea was actually the key in solving the orientation problem inside the heart. I mean, this plus tens of millions of bucks, which you have to put into, to develop it and take it through human trials. But the seed was the simple idea. Okay, so this is the assignment. I'll bring you your next week's assignment. As I said, every one of you will get a hard drive, and you have to do some investigations of the actuator. But you'll have lots of time to do that. I'll give you a full month to do that, so you don't have to worry about scheduling. Okay. So what students tend to do, which is not good, because if they learned about something, like they learned in a lab about a laser interferometer, which cost a fortune, so if they ask something which can be solved with a very simple solution, they say, why not use a laser interferometer? Why not use this? Why not use that? So, you always have to supply the simplest solution. The fact you learned about all these very complex solutions, doesn't mean you have to use them. You always start thinking, what is the absolutely simplest solution? Okay, and if it doesn't work, you escalate. Okay. You know the saying, if you have a rope, you don't have to hang yourself. So, just because you know the solution. Okay, so now let's move back to actuators. So we discussed moving coil actuators on Tuesday, and this is still probably the most popular actuator there is in linear actuators, maybe not in motors, but as I said, disk drives, meters, galvanometers, all kinds of specialty actuators. Moving coil is still a very, very popular actuator. Now, what happens in a moving coil actuator where you clamp down the coil that it can't move? If you clamp down the coil, there are still forces between the coil and the magnet. So if you clamp down the coil, the magnet will try to move. Right? Because there is a force between the coil and the magnet, and then it becomes a moving magnet actuator. But of course, to design it, you want to change the proportions. You want to make the magnet small and light. So in a moving coil actuator, typically we said you'll take a big magnet. Say if it's rare earth magnets, you wouldn't have to be so big. But traditionally, like in a meter, you took a big magnet, okay, a big magnet, NS, and you had a small coil. This was a coil which rotated. Now if you clamp the coil, the magnet would want to move, but it will be not optimized. So if you wanted to make the same thing into a moving magnet, you'll make a big coil and a small magnet, NS. Okay, so now if you energize the coil, it will pull in the magnet. Or you can make it rotate, for example. You can do the same thing. You can have two coils and have it rotate. So if you have a coil here and a coil here, and you put a magnet at an angle, NS, on a pivot, so if you magnetize this, and this will be S and this will be N, the magnet will rotate because it will want to align itself with N facing S. Okay? But in a moving magnet, you'll always make the coil big and heavy and the magnet small. Why would you make the coil big and heavy? Why not leave a teeny coil? So yes?
There's a larger moment of inertia, so you're more likely to move the magnet as opposed to...
Yeah, but even if you clamp the coil, let's say the coil is clamped, it cannot move. When you look at moving magnets, the coil seems to be heavy and big. If you look at moving coil, the coil is tiny. Yeah?
on
Some of it, but think of the limit. What were the limits on a moving coil actuator? The first limit was heating, current density. If you overcame this limit, then there was demagnetization, right? But if the coil doesn't have to move, why not make it from very heavy wires, and you'll never have a limit? Because the only reason for this calculation we did Tuesday was that we had to optimize the ratio of mass to force. But if the coil doesn't have to move, the mass doesn't matter, so why don't you make it from very heavy wire? There'll be very little losses. You know, you'll never have a limit. Or you'll never have a heating limit. So in a moving magnet actuator, the only limit is demagnetization. Because a magnet has to be small so it can move easily. But if you have a big coil with a big current, you can reverse magnetize it or demagnetize it. Okay? So on moving magnet actuators, there is only one limit, demagnetization. But the limit is severe, because the magnets are typically small, otherwise they cannot move fast. Okay? Now, it turns out, strangely enough, that the maximum acceleration possible is about the same. And what's even stranger, that if you take moving iron actuators, which we haven't discussed yet, they also have about the same limit. So basically, we talked about the limit being in the order of 100 G for continuous motion, okay? Not peak. Now this one doesn't have any difference between the peak and continuous because there's no heating limit. Demagnetization is instantaneous. So the limit of this type of actuator for continuous motion, what's called steady state, and pulse is the same. It's always demagnetization. But let's say we talk about steady state. On the moving coil, we said the limit was about 100 G from Tuesday. Strangely enough, this is also about 100 G. I mean, I'm talking order of magnitude. The exact numbers depend on how you cool it, how you build it. But this is also on the order of 100 G. And the moving iron one, which we haven't discussed, is also about 100 G. So it means there is no huge performance advantage over one actuator over the other. The moving iron looks exactly the same, but you don't magnetize the core. It's basically a solenoid, right? If you take a solenoid, you can pull in the core without magnetizing. It doesn't have to be magnetic, it's enough to be steel. Say if I have a solenoid here, and if I turn it on, say this is with AC, I can just make it pull in the core, okay? But this is not magnetized. So that's moving iron, which we'll discuss soon. Okay, so now, if all three, this moving iron looks the same like this, moving coil, moving magnet, if all three are about the same performance, why do we need three? Okay? Like, is there any advantage or disadvantage that make us choose one over the other? It's a bit similar to the discussion we had on capacitive sensors versus inductive sensors. Both do the same, but sometimes you use one, sometimes you use the other. So the question is here, if they're all doing the same thing about the same performance, by the way, same cost as well, because all of them have a coil and a magnet or a coil and some steel. The moving iron is a bit cheaper but has other problems which we'll discuss. So the cost is comparable, performance is comparable. Why do we need three? Yes?
The difference between moving iron or moving coil and moving magnet is that you have to change the polarity of your coil every time you make or making rotary components. So you have moving wear.
Okay, so let me understand what you're saying. You're saying if between moving magnet and moving iron,
Moving coil.
coil. So if you want rotary motion, well, it's not exactly correct, because we haven't talked about motors yet, but if we want rotary motion in this one, we have to do something called a rotating field. Okay? Now, if we want rotating motion in moving coil, we can do either a commutator, which we haven't discussed, or we can do what's called an induction motor. So let's not get into that because that's the subject of next week's. But actually both of them can be converted to rotating motion, and in a way you can do electronic commutation and so on. So that's not where the difference is. The difference must be somewhere else, because even for linear actuators or angular actuators, some people use this, some people use moving coil. So there must be some other fundamental differences. So again, be practical. Think of if you had to manufacture those things, just think of practical things.
Certain geometries might be easier with different...
Sometimes geometries, but there is two fundamental reasons. The first fundamental reason, moving coil also always needs some flexible wire to connect to the coil and flex. If you look at the loudspeaker, which we saw Tuesday, there's two thin wires connected with the coil. These wires bend all the time. If you have a disk drive, there's some wires connected to the coil. Now these wires can be made beautifully flexible, but they still flex. So if you have something which has to move constantly back and forth at high speed, eventually the wires will break. An example of that is, say, a laser scanner. You know these laser light shows, where you take a laser and move it with mirrors to paint things. I'm sure you've seen a laser light show. These lasers have to scan all the time at very high speed. So eventually the wires will break. Now moving iron have no wires. So anything which has to move continuously, say a sine wave to resonate or rotate, anything which has to move continuously, there's nothing to break here. And we already said that in a moving coil we have some advantage for some peak pulses. But if something moves continuously, it's always working steady state, so the fact that this is not suitable for very high pulses doesn't matter, because anyway we only use it when you have to move continuously. Okay? So this big advantage here is no wires. Okay? The disadvantage here, that the pulse rating is no bigger than the steady state rating. I'll summarize it at the end in a table. But right now, when we talked about moving coil, we said it's 100 G sustained. But if you want just a single pulse, you can drive it with 10,000 G until you reach demagnetization limit. Okay? Now here, if it's 100 G steady state, it's also 100 G pulse, because the magnet is small, you can easily demagnetize it. Okay, so basically the disadvantage here is no overdrive. Okay, so I'm writing on top advantages, and here on the bottom I'm writing disadvantages. So this one is no wires but no overdrive. These two are the same. So if I put here moving coil, this is moving coil. So moving coil, disadvantage is wires. It's exactly the opposite. And advantage is overdrive. Okay, and if I add here moving iron, so moving iron is the same, it's just a solenoid pulling in a piece of iron. Okay, so how does this look? How does this look in terms of properties? Can I overdrive this with a huge pulse? Yes or no? Come on, wake up. Yes, because there is no magnet. I cannot demagnetize it, and the coil is not moving. Because the coil is not moving, I can make the coil very heavy wire. So I can have a massive coil, very heavy wire, there is nothing to demagnetize, I can overdrive it with a big pulse. I mean, there are some limits because the iron will saturate. So maybe if I overdrive it, at some limit the force will not go up anymore. But there is no damage at all by overdriving. So on the advantages, I can overdrive. Okay. Now, there is a disadvantage which relates to what was mentioned before about the motor, about the direction. Because this one, if I put one polarity, it will pull in. If I put another polarity, it will also pull in. Right? So if I wanted to push out, I can't. I can make one differential. I can make one with two coils and two slugs. So if I want to push this way, I'll energize this coil. Right? I can build it mechanically, so it will be directional. Or I can bias it. I can bias it halfway, and then I can pull in or out by changing the current. Okay, this actually has another big disadvantage, which we'll talk about later, and that it's non-linear and has some other problems. So the biggest disadvantage of this is actually the fact that it's non-linear, and we are going to talk a lot about it, what it means. But let's not deal with that now. So let's deal with this versus moving coil. Okay, this is a magnet. So it's clear that in applications which have to scan continuously at high speed, I would pick a moving magnet. At applications which I need the capability to overdrive or momentarily have high acceleration, I would pick this one. Okay? And in applications which are neither, I could pick either one. Okay? Now, in a lot of cheap stuff, you see this moving iron. Especially if the actuator doesn't have to be linear, doesn't have to be positioned. In actuators which are on-off, so a lot of actuators are on-off, like a relay, a solenoid, a door lock. In all simple on-off actuators, you always see this. You never see moving iron, you never see moving coil. Why is that? And I'll give you a hint. It has to do with sealing. Some of these actuators have to be sealed, some don't have to be sealed. And think about it, why? So, okay, imagine there is iron dust. Imagine the machine shop, there are metal chips. Now, what happens if moving coil or moving iron were not sealed? They'll stop working, because all the metal chips and metal dust will be attracted by the magnet, and in no time the magnet will be covered or the gap will be filled with metal chips. Okay? So any actuator which has a permanent magnet has to be fully sealed. And sealed means money. The sealing costs money, and because it has to be sealed, it doesn't cool as well. It's not ventilated. I'll give you another example which will come back when you talk about motors. All power tools you buy in the store don't have permanent magnet DC motors. Wouldn't say all, but 99%. So if you buy a power saw or a drill, they have a motor which is wound, but it doesn't have a permanent magnet. The permanent magnet makes the motor simpler, and we'll discuss it in the weeks to come. Now, the reason they don't have permanent magnet motors is they want to ventilate the motor. They want to have lots of holes so air can cool the motor in order to make a smaller motor to save money. Okay? But if you ventilate the motor, you cannot have a magnet inside, because the metal chips will stay. So that's the reason. So basically, the disadvantage of both those, they have to be sealed. And this, the advantage is it can be ventilated. And that's a big advantage, because ventilated means you can use thinner wire, it gets hot, somehow the airflow will cool it. So it's a big cost advantage. Not only do you save the box, you save on the wire, you save the material, because you say if it gets hot, somehow the airflow through it will cool it. Okay? Very important. Okay, so now we are going to move. So I'm not going to give you an analysis, mathematical analysis on the moving magnet, but what I do want to talk to you a little bit is about magnetism, because as I said, the limit on this is demagnetizing, because the magnet is small, and I want to make sure everybody understands what magnetizing and demagnetizing means. Because from my experience, no student knows anything about it, although they learned it in Physics 101, but 4 years later I never met a student who remembered a thing about magnetization. And that's very important, because all actuators rely on magnetization, so it's worth a refresher. Okay? So typically magnetization is represented on a graph called a BH curve. Okay? Okay, so H is a magnetizing force. So if you have a coil, H is the same as Ni. How many amp turns? And I already mentioned to you before that when you think of coils, the best way to think of it is like a solid block which carries a current of Ni. If it has N turns, each one carrying I, just look at it as solid blocks as a current Ni. So this is a magnetizing force, okay, and measured in Ørsted, named after Ørsted, who started this whole field, of course, and B is the magnetic field which the magnetization results in, okay, and so this is measured in Tesla in MKS units, okay, measured in Tesla. These things have, in some books you'll see terms like Gauss, because there was an old system and a new system, okay? So the old system measured the field in Gauss, and the new system is Tesla, okay? It's 10,000 Gauss to the Tesla. So if you look at an older book, you'll see the term Gauss for B. And some specs are still in Gauss when you look in catalogs, but basically you should be used to Tesla. So a good number is, in most materials, it's hard to get much above 1 Tesla. If you take a piece of steel and magnetizing, at some point the steel itself will reach saturation. When you try to magnetize it more, it will refuse. So what happens when you start magnetizing a piece of steel, you see some strange behavior. There's a little kink here, and then it magnetizes very nicely in the linear range. Linear meaning if you double H, you double B. Okay? And then it starts saturating, you increase H. Increasing H meaning you have a coil and you increase the current. And you measure how magnetized that is. Okay? And how magnetized that is also related to the force you can get. Because if it refuses to magnetize anymore, it means it wouldn't produce any more force, right? Because the force is interaction between two magnets. So at some point it starts saturating, and once it's saturated fully, it just behaves as if it was air. Because even in air, when you keep increasing Ni, the magnetic field in air will go up, but at a very low slope. Okay? So the slope for air, say if this was air, the ratio between B and H is called mu. Okay, so mu is B over H, or B is mu H, it's the same, B is mu H. So that slope for air is called mu 0, and it's quite low. Mu 0 is 4 pi times 10 to minus 7. Okay? While the mu of a good magnetic material can be 10,000 times or even 100,000 times more than air. So that slope of a good magnetic material is thousands, 10,000, maybe hundreds of thousands times more. It's a huge difference, okay? So, and this slope is referred to by mu r times mu 0, where mu r is a relative improvement. It's exactly like we talked about capacitance. We said it's K epsilon 0. Epsilon 0 is air, and K is the dielectric constant. How much better than air it is. So here, mu r is how much better than air it is. Okay? And this number can be very large, so I didn't draw it to scale. If I drew it to scale, mu 0 it will basically merge into the x-axis. You wouldn't see it. It is so low. And this slope is 10,000 times more. Okay, there is a little phenomena here, which is usually not mentioned in books, that if you really magnify what's happening around the 0, if you magnified it a lot, you will see that for most materials, the line doesn't cross 0 like this, but for most materials, the line actually does a little thing like this. So near 0, when you increase the magnetizing field, for a little bit nothing happens. That's a big problem if you try to use it as shielding. There's only special materials which don't do that, and I mentioned when we talked about shielding, I mentioned mu metal, which is a special material which even at very small fields starts magnetizing. Good. Now, can somebody explain this behavior? So when you look at this and you plot it, and it's very easy to do this test in the lab to plot it, and you see this funny behavior. It has this little kink here, and then it saturates, and you say there must be some simple explanation. Why do magnetic materials behave like this? Okay, so now let's test your memory. Why is that? What's the explanation behind this curve? Okay, speak up, please.
You said it's like static friction?
Static friction of what? The analogy is not bad. The analogy is not bad, but friction of what? What is sliding?
The domain center.
Ah, very good, very good. You see, you got it. So it turns out that if you look inside the magnetic material, it consists of many zones where each one is a little magnet. So if you take a piece of steel and you look inside, and it turns out you can see it even with a naked eye, because this magnetic domain, some of them could be big. You can see it with so what you see is you see some little boundaries. They look quite random. They are not like crystals. They are not always regular like crystals. They could be quite random looking. And each zone is a little magnet, so which is magnetized this way, this way, this way, this way, but the magnets are randomly oriented. The magnets are randomly oriented, so the total sum is 0. So if you take a piece of steel, it's not magnetic, because the sum is 0. Now when you start magnetizing it, these domains start rotating inside, and when it's finally magnetized, these domains physically rotate. Okay, and when it's fully magnetized, all these arrows point one way. Now once these arrows point one way, it cannot get any more magnetic because it's already all aligned. And that's this point. The all domains align, it saturates, you can't do anything, it behaves just like air. Now the reason why it doesn't start rotating at the beginning, because these domains have some stiction, just like static friction, so when you increase the field a little bit, they don't move yet. If you increase it a little more, they start moving, okay? And the most interesting thing about it is that these domains are quite big. As I said, they are from microns to almost a millimeter, and you can see them with the eye. The way you see them, you polish the steel and put on it a liquid which has very small particles of iron. And these particles of iron, just like iron dust is attracted to magnet poles, if you put this liquid on it, these particles will attach themselves to the domain boundaries. And you can actually see the domains with a low power microscope. Okay? So, it starts off with a bit of static friction, then the domains rotate until all of them are aligned. And there's two very interesting things. These domains are odd shapes, so when they rotate, they don't quite fit. So actually the dimension of the material changes. So when you magnetize something and you measure it, it changes dimensions. Okay? Usually it shrinks. Most materials shrink once the domains rotate, they fit better and the material shrinks. And this phenomena is called what? You learned it a few years ago. Pardon? Very good. Hey, somebody remembers this physics. Okay. So, when the domains rotate, they fit a bit better, the material shrinks, and that's called magnetostriction. And all of you noticed it, because when you walk by a power transformer, you hear, right? Every big power transformer has a hum. The hum you hear is the steel core of the transformer shrinking with a sine wave. Okay? So what is the frequency of the hum? No, 120, because it shrinks in both directions. So if you have a sine wave, the transformer core will shrink here, but will also shrink here. So same as the frequency of the ripple of the light, it's 120 hertz. Okay? And in Europe it's 100. Okay? Why is the line frequency in North America 60 hertz and in Europe 50? Let's see if you know your history of science. Tesla. The fellow who invented the polyphase system was Nikola Tesla. He had the patents on it, and he was a bit crazy. He believed a person should never work with numbers which don't divide by 3. So when he licensed his patents to Westinghouse, he stipulated they have to use a number divisible by 3. And Westinghouse argued, because they said it will be a disaster, nothing in Europe will be compatible. But Tesla said it's more important that divisible by 3 and forced them to use 60. That's the reason why there is 60 hertz. Okay? But anyway, let's get back to the subject. So this is magnetostriction, it caused by the domains. Okay, now, second interesting thing about magnetization, that if you put a microscope to this graph and examine it microscopically, you will see that actually it's not a smooth line. It's actually made of all kinds of random little steps, not always the same size. And this makes sense because the domains, when they rotate, some snap and then the other one snaps. They are not like ball bearings which can rotate smoothly. They are irregular shape. So when you try to force them to rotate, one jumps and the other jumps and the other jumps until they all align. Right? So the magnetization isn't built up completely smoothly. Each domain which snaps adds a little jump. And now, something I don't expect you to know, what is this called? This effect that this graph is actually made of little steps. Okay, that you wouldn't expect you to know. That's called Barkhausen effect. But this you probably didn't learn in Physics 101, so I don't blame you. Okay? So, you can listen to it when you put another coil here. When you put another coil on a piece of steel when you magnetize and connect this coil to headphones, and listen, when you magnetize a steel, you hear tick, 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 tick. You can hear each domain jumping. That's Barkhausen effect. Good. So, we explained the domain business. One good analogy of a magnet, which will come handy when we talk about motors. The best model for a magnet is you take a bag, or best model for magnetic material. You take a bag and you fill it with a whole bunch of small magnets submerged in oil or grease. And that is the best model. When you start magnetizing this whole bag, the little magnets inside will act like the domains. At the beginning nothing will happen, and submagnets will move and more magnets will move, just like the domains, and you'll get this graph. Okay? Now, the reason you need the oil in the model is that when you try to do it faster and faster, you need more and more energy, because there is some viscosity built in. The whole thing behaves as if these things are floating in thick oil. So when you do it slow, it takes one power, but if you do it faster, you seem to take much more power because of the friction losses and the behavior as if it's sitting in oil. So a very good model is a bag of little magnets sitting in oil. That models very well the behavior of a piece of steel. Good. So let's continue with this. So the reason I'm going over all this, because we need to know the theory of magnetism both for actuators and for motors. Because we need to know it here for actuators because of these demagnetization problems. So this is, this is H, this is B. So now we understand more or less why it looks like this. The reverse is symmetric, of course, because this piece of steel doesn't have an up or down. So if it magnetizes one way, if you reverse it, it will magnetize the other way. Now, what happens now if you reduce? So far we increased H. We went up like this. The slope here was mu r, mu 0. The slope here was mu 0. Now we're reversing the current. What happens? Yes?
We get hysteresis.
Very good. See? So it doesn't want to repeat this way because the same stiction between the domains, which took some effort to make them snap, when you reverse, they don't want to snap back. They're stuck to each other. Takes some effort to overcome to make them snap back. So when you reduce H to 0, it actually comes back like this, because when H is 0, some domains are still stuck and oriented. The net magnetism is 0, and of course if you keep reversing H, it will do this, eventually do this. If you increase H again, it will do this, and it will do this. So if you keep reversing H back and forth, in other words, if you drive the coil with AC, you are traveling on this axis back and forth, okay, you will get a loop, which I'll draw in a heavy line. And this loop is a famous hysteresis loop. Okay, and if you increase the frequency, like if this is a coil, say, driven with AC, So the magnetization looks like this. But if you keep increasing the frequency, the loop will actually widen. And the loop will widen because of this viscous effect I mentioned, similar to having oil inside. Is that clear? Good. So now you can understand how you make a permanent magnet. So obviously if you want to make a permanent magnet, you're looking for a material where this is very high. You're looking for a material which has a huge hysteresis. So when you take away the coil, it stays magnetic. Okay? Now if you're looking for an electromagnet or a motor, you're looking for the opposite. For something, when you take away the coil, it will come back to zero. So this means that you have to select the material by the application. So this is B, this is H. So if you want to make transformers or motors or whatever, you're looking for a material which has a very, very narrow hysteresis loop, because it turns out that this area of the hysteresis loop, this is actually equal to the lost energy per cycle. I'm not going to get into that because it will take a long time. It's not so important, but basically you can intuitively see that if you drag something and drag it back, and there is friction, there is energy lost. Imagine if I move this back and forth, and there is friction and hysteresis, there is some energy lost. And the more it wants to stay the way it was, and I have to push it harder to bring it back, the more energy is lost per cycle. So the area of the hysteresis loop is the energy lost per cycle. So if you want to make a transformer or an electromagnet, you want a narrow hysteresis loop. Okay? Because you don't want to lose every cycle a lot of energy, because it will get hot. But if you want to make a permanent magnet, you're actually looking for something like this, that as soon as you take away the magnetizing current, it will stay magnetized. So basically you're looking for something ideally which looks like this. So this is for making a permanent magnet, and this is for making, say, a transformer or electromagnet or a motor, anything but a permanent magnet. Okay? So if you want to make an inductor, this is very bad for an inductor, because once you use the inductor, it will stay magnetized. Right? So for an inductor, you want this. Okay. So one thing you should know is that there are many exotic materials to do this, but there are some common very good materials. So to make narrow hysteresis loops, all the coils and transformers and everything in the world which needs to have narrow loops is made from steel with 4% silicon. It just turned out it was found 100 years ago. It's a very good material. This material is very cheap and has very reasonably low losses. There are better materials than that, some nickel alloys, but all the industrial stuff is made from this. Okay? And that you should be grateful to Steinmetz. Steinmetz is the first scientist who understood the whole AC theory. The reason General Electric for years dominated the business of power stations, generators, is because of one man, of Steinmetz, because he figured out all these things we're talking about, and that's why GE knew how to build all these motors and transformers and generators. Okay, now if you want to do this, if you want to make permanent magnets, today the best material is what's called rare earth magnets. You probably heard the term rare earth. A year ago, China refused to sell the rare earths. There was an upheaval because it's a strategic material. Okay, so this is today, the PMs are made from rare earths, for example, neodymium iron or samarium cobalt. These are all called rare earth magnets. Okay, NdFe or samarium cobalt. So these are rare earth magnets. So the two materials you have to know: for magnets you use rare earth magnets, for everything else you use silicon steel. For special high frequency you use ferrite. Ferrite is combination of carbon and iron, typically. Could be carbon and manganese, carbon and nickel. And that's a material which doesn't have such a high saturation but has very low losses. So anything high frequency is ferrite. Okay? And that's about it. That's about what we need to know about magnetization. So demagnetizing means that something is magnetized here. Like you have the magnet of a moving magnet actuator, but you overdrive it very hard. And if you overdrive it very hard, what can happen? You can take it down all the way here, okay? And you can take it down, let's say, to here, and then it comes back through an hysteresis loop, and suddenly it comes back to zero. Because if you overdrove it all the way to here, it will come back to a reverse polarity magnet, which is not so bad. The actuator will just reverse. But if you overdrove it to here, and then it will come back to zero. Because it always follows, it goes up, then it goes back, and then it comes up in a different curve. So if you overdrove it to here, it will come back to here, and so on. Okay? So in other words, if I'll trace it, if I start from here, I go up. If I reverse, it follows an hysteresis loop. If I reverse again, it keeps following this loop. But if in one of the cycles I don't go all the way down, I go to here, it will do this, okay? And then if I go less to here, it will start doing a different loop. Okay? Because this loop and how big it is depends on the history, where I started from. So obviously you are changing it. If something was magnetized at here, it's a permanent magnet, and if you don't overdrive it, it will fluctuate around this area. But if you overdrive it, it may end up at a totally different area in the BH curve. And that's called demagnetization. Is that clear? Good. Okay, so this is the limits of moving iron actuators. Now I want to show you a little demo, and we'll discuss it next week, but I want to show you this demo and so you can think about it. Why is that? Okay, so what we'll do okay, we have an electromagnet here. Okay, we have to wait till it power up. We have an electromagnet here and a spring. So basically we have this thing, moving iron actuator, we tie the spring to it. Spring is linear, kx. If it was a moving coil actuator, if we double the current, the spring will stretch twice as much, right? So let's see what happens with a moving iron actuator. Good. So now go to this. Beautiful. Should autofocus in a minute. Bellissimo. Okay. Okay. See, it's autofocus is playing. Moving coil actuator. Okay. Okay, good, but it has some problems. Good. Good. So now what I'll do is I'll increase the current and watch what happens. So the spring is linear. If I increase the current, I would expect the spring to stretch, and it starts stretching nicely. You see it's moving a bit. See, the spring is stretching, but then see it's stretching, but then bang. So somehow it seems to be very strange. At the beginning it behaves maybe not linear, but it seems to be proportional at least. See, it's moving, but at some point, instead of keep moving, it just jumps. Okay. Now let's try it with AC. So I'm just switching it from DC to AC. The beginning keeps moving a bit. It's making noise. Okay. This noise is not magnetostriction. Part of it is magnetostriction, but part of it is just the force is fluctuating, so the spring makes it vibrate. Now it looks a bit better. I can move it a bit more, It drives the autofocus crazy, but anyway. See, so I can move it a bit more, but at the end it jumps. But here it seems to jump much later. See, it's still okay, and then jumps. Okay? Okay, so that is Okay, so this is the reason why moving iron actuators are not so popular. Exactly because of this jump. Okay, now let's say you say, okay, maybe there's something wrong with this, I don't know, maybe it's some special solenoid. Let's try it with another coil, just to make sure the effect is real and universal. Okay, so I have a little coil here, a relay coil. So let me hook this up and see if the behavior is the same. That's a kind of little coil you'll find in relays. Okay. This problem is this clips are bad, so let's try it one more time. Okay, so now we try it here. Now can we see it? Let it autofocus. Okay, so wait. Okay, so what I'm doing again, I'm changing the current in the coil. So watch, at the beginning it's moving, you can see the armature moving, but then it jumps. Seems to be the same behavior. Linear, or not linear, but proportional range, and then jump. Let's try it with AC. Same thing, proportional, but seems a bit better. I can come a bit closer, and then it starts doing funny things and jumps. So there is a range which seems controllable, and then the reason it doesn't jump completely, remember it's AC, so AC goes through 0, so each time the AC goes to 0 it lets go. If it's fast enough, if the armature is fast enough, it will just let go at these places. If the armature is heavy, it will stay stuck, and there is another reason why they stay stuck, and we'll talk about it later, because this also has special short-circuiting terms which prevent the zero in the magnetic field, and we'll discuss it next week, because that's a separate issue. But basically we are seeing that these two things behave more or less the same. You get a controllable range which doesn't look that big, and after that it snaps. Okay? So let's see if somebody here can think about it. What causes this strange behavior? Yes. Okay, so you started off correct, saying there must be something non-linear in the force versus the air gap. Maybe there's an r squared, x squared, which is correct. But x squared is a continuous monotonous function. So why would it jump? You would expect it, okay, not to be linear, but at the beginning to move less with the current change and then more with the current change, because the force equation is non-linear, as we'll see next week. But why does this change behavior? It's non-linear and then it jumps. So that's a question, yes?
Get within range so that there's less leakage, and then the force is stronger and it just...
But it still doesn't make sense, because it's a continuous function, right? The air gap and the leakage, everything is continuously changing. As I do this, it's true the force now increases not linear but square law, but there is no singularity. Like in the graph, it's The graph is 1 over x squared, as we'll derive soon. So there is nothing in the graph which says it should jump. There's no step function in the graph. Yes?
There's positive feedback because as the force increases, the iron goes closer.
Ah, very nice. So it turns out that, which we'll prove next week, that any actuator which has inverse square law type, like 1 over x squared, or higher order, 1 over x cubed, 1 over x4, has to jump. And the reason why it has to jump, it reaches a point of positive feedback. So at some point, a slight increase in current will decrease the gap in such a way that it will cause a much bigger increase in force than the resistance of the spring. So it will move more and the cycle will repeat. Okay? So it will get to a positive feedback mode and it has to jump. And this phenomena is called snap. And this exists in all 1 over x to the power of n actuators. Where is a chalk? And that is a very important phenomena, especially in micro-machined devices. Because micro-machine devices, the best way to get force is electrostatic. And an electrostatic actuator has the same type of behavior. It's 1 over x squared. So in order to show you the proof of that, since I don't have time to, I'll just start the proof today and we'll continue the proof next week, but I'll just show you the principles. So there is a general methodology how to analyze actuators, and I already showed you a couple of times how it's done. You derive a formula for the energy of the actuator, and then you take the derivative of the energy versus travel. And that is kind of the standard way of doing it. There are other ways to analyze actuators, but this energy method is the best because it works for all kinds of actuators. So you have just one method. It works for hydraulic, mechanic, capacitive, inductive, so you don't have to know different ways of analyzing. So the way you analyze what happens, you find out, first you derive the formula for energy, and then you differentiate it. So maybe we can start with a capacitive actuator, because that's simpler. The four equations are simpler than we can do it for an inductive actuator. So what is the energy if you have a capacitive actuator, which means you have a plate which can bend, or maybe you have a plate which is spring-loaded like this, and you have a ground plate. This is ground. So there is a capacitance C between the plates. You connect a voltage here, the plates are attracted. Okay? And I mentioned to you this projector works like this. Inside this projector are a million of those. Okay? So what is the energy in a capacitor? If I charge it to voltage V, what is the energy in a capacitor? Come on, that's for sure you learned. Yes?
1/2 CV squared.
Good. See? Second score today. Very good. Okay. So 1/2 CV squared. And what is the C of two plates which are separated by distance x and the plate have area A? So what is C equal for this capacitor? I gave you the formula months ago. Say it again? Yeah. So this C, now C is epsilon 0 times epsilon r if there is a dielectric A over x. Okay? So the energy in a capacitive actuator is 1/2 epsilon 0 epsilon r A over x times V squared. So the force is the derivative of the energy to dx because you can also take the derivative of energy to V or the derivative of energy to other parameters, but I'm only interested in derivative to X. So everything is constant here except X. So it's 1/2 epsilon 0 epsilon r V squared A, derivative of 1 over X, which is minus 1 over X squared. I'm ignoring the minus because it's just the direction of the force, X squared. Okay, so this is a force in a capacitive actuator. Okay, and you can derive in a very similar way as a force in an electromagnetic actuator, but I wouldn't start now because I'll run out of time, so we'll cut it off here. We'll continue Tuesday, and then we'll discuss SNAP.